All right, Chapter 5 is going to finish us off. 2 sections in Chapter 5. 5.1, we're going to be looking at systems of linear equations. And in particular, we're going to be looking at 2 equations with 2 unknowns at the same time. So for starters, a solution to a system of linear equations, is the set of all ordered pairs that satisfy all the equations in the system. So if we're working with 2 equations like this one, where it has x plus y equals 1 and 2x minus 3y equals 8, what we're looking for, what we want to know on this particular problem is whether or not the point that they're giving us, this negative 1, 2, is a solution. So in order to be a solution, it means that it has to work, that is, it has to make both sides of each equation equal to the same thing. So in order to test that, we simply evaluate it into our equation. So the first equation is x plus y equals 1. So if this equation is going to work, x would equal the negative 1, y would equal 2. And it's sort of like you're putting a question mark right here. What does negative 1 plus 2 equal? 1, right? So it worked in this equation. This is a solution. Now, each equation has infinitely many solutions, so it's not surprising that we would find a solution. However, it may be the only point that they both have that work. That's something that's unique about systems of equations, is that there's often only one point that is a solution to both equations. So this one worked in the first equation. That may or may not mean that it works in the second. So we tried in the second equation. So 2x minus 3y equals negative 8. So again, our x is supposed to be negative 1, and our y is supposed to be negative 2. Right? And we're asking ourselves this question, does this equal negative 8? So 2 times negative 1 would be negative 2.
Why is it negative 2?
It's not supposed to be. You mean this piece right here. That one right, oops, come on, get my eraser out. That one, did you get that? Is that what you meant, David?
Yeah.
Thank you, I just got sidetracked. Okay, so the negative 2 at the beginning is 2 times negative 1, and then we have negative 3 times 2, which is negative 6, thank you. And negative 2 minus 6 is, it really is negative 8. It checks out again, right? It works in both equations, so the question that we were asked is it a solution? And the answer is yes. If it failed in either equation, you wouldn't even need to test it in the second one. You just need to test it in one at a time. If it succeeds, you test it in the other one. If it fails, you're done, and the answer is no. So since it succeeded in both cases, the answer is yes. So testing for it being a solution is pretty straightforward. But what we're going to spend the most of our time doing is actually finding a solution when we're given a system. So we're going to look at 3 different types of ways of finding solutions. They do all have sort of benefits and drawbacks. So the graphing one is very nice and beneficial for those of us who think and see things very visually. One of the drawbacks, however, is that unless they cross at a nice, neat whole integer value, like at the corners of something, it's sometimes really hard to tell what their actual answer is. So it can be a little bit elusive. As we're taking a look at these, you can graph them in many different ways. I'm going to go ahead and solve each of them for y as the way that I'm going to graph them. So if I were looking at this equation and solving it for y, I would move the 2x to the other side. So y equals negative 2x minus 1. And on the second one, I would shift my x to the other side. So it would actually be a positive x plus 5. So those are the 2 equations that I'm going to graph. Because I'm not working on grid paper, it's going to make it harder to see unless we just happen to plot a point they have in common on both of the graphs. So if you have grid paper, use it. That's fantastic. If you want to get some grid paper or print it off of the internet, right, just as images from the internet, you can do that. You're not going to have a whole ton of these, though, so it's not like I'm asking you to print off a bunch of things. The first one is y equal negative 2x minus 1. So negative 1 is where it crosses the y-axis. and it has a slope of -2, which means it goes down 2 and right 1. And we're going to try our very best to give it some scale that makes sense. And then I'm going to also do the other side, sort of the left-hand side of the graph, by going up 2 and left 1. So I don't necessarily need 3 points, but the more points I plot, the more helpful potentially it's going to be in finding the location where these two graphs cross. Because that's what I'm looking for. I'm looking for the graphs to cross one another. So my first graph is this line. I'll get it shifted over after I've drawn the scale right. Oops. Okay. Try again. Like that. So that's my first line. I did it in yellow. I'll do the second line in green. So the second one actually crosses where? Where does it cross the y-axis, this equation? +5, thank you. You guys are not very talkative today. +5. And its slope is what? It's 1, right? So I'd be going up 1 and right 1. That's actually true, though not real helpful for graphing purposes to come over here because it's not in the direction of the yellow line. So actually going left 1 and down 1 so that I can shift towards the yellow line might be a bit more helpful, like this. So as I'm working my way along, if I've graphed it well, we can see they do in fact cross, right? And it might be easier for us to plot a few more points to see for sure where they cross. So down 1 and left would be here. Down 1 and left looks like it might be here. So my graph is not drawn well, but I think that that point is at the height of 3. And it's to the left 2. So I believe it's at -2, 3. Let's see. Nope. -2, 4. Did I not get my... Oh, I didn't get my graph. That's what's wrong. Let me shift that. I put it at the wrong spot, didn't I? I put it at... Let's try it again. I did draw it right. No, I can't undo it. Okay. Oh, no, I had it right. I just have it wrong on my paper. That's what's wrong. That's 3. And then there's 1 crossing over here. Oh. Can you see the problem with graphing? I'm struggling and I know what the answer is supposed to be. All right, so if I'd gone up 1 and left 1 again, let's see if I can get them drawn in here at least so that it makes sense. It should be right here, and that should be my graph of my point, and it's not. So let me see if I can shift it so it looks a little bit more realistic. This one is actually over to the right 1, and that's actually one of the points here as well. That's where it's supposed to fall. If I had a grid, it would be easier to see it, but that is my point where they're crossing. So it is -2 and 3. And we could check to make sure that it works inside of each of our equations to confirm that we do in fact have it crossing in those locations and all of that. But this would be what graphing would look like. If you're using a graphing calculator and you can go ahead and solve them like we did here for the y equals, you can also see where they intersect. There's some intersect features inside of the graphing calculator. It's a fabulous way of checking to make sure that you're getting the right thing, and also to get sort of a visual imagery of the equations. But again, it's very tricky because you have to draw so precisely to see the locations where they're crossing one another that makes it not so usable. And in fact, if they are actually crossing at anything but an integer value, it's practically useless, right? If they crossed it like 1/2, 3/4, I mean, really, your graph's not going to be able to show you that. All right, so the second method that we're going to look at for solving is solving by substitution. So I'm going to run through the basic gist of substitution. Substitution and elimination are going to form the basis of what we need in section 5.2 as well. So they're really important. To solve by substitution means to solve for one variable in one equation, and you get to pick. You get to pick the equation, and you get to pick the variable. And sometimes there's a nice choice, and sometimes there's not so nice choices. So if we were looking at this equation, it would be lovely to solve for anything but the x in the first equation. What is it about the x in the first equation that makes it more difficult to solve for than any other variable? It's got a coefficient of 2. So any of the others that have coefficients of 1 or -1 are much easier to solve for. So there's often a nicer choice than others for our starting with solving with substitution. However, sometimes they all have coefficients that are not 1. Then substitution just is not a good choice, period, right? So again, it's a drawback. It has its good things, but there are some things that make it not so useful as well. So the first thing is to solve for one variable in one of your equations. The second thing is to substitute for that variable in the other equation. So we're going to do a substitution step, hence solving by substitution. Once you do that, you have an equation that only has one variable left. So you're going to solve for that remaining variable. And then you're going to substitute or back substitute, we sometimes call it, the resulting value into one equation to solve for the other variable. And again, you have choices. So our next example that we do would be terrible to do if we were doing it with graphing. I'm not going to get an integer value. So if I tried this with graphing, I would be really quickly disappointed. There is a very natural equation to solve and variable to solve for, though. What would you like to solve for one variable? Yeah, the equation that's easiest to solve is the second one with the value x because it has a coefficient of 1. So we're going to start, this is sort of step 1. We're going to take that equation x plus 3y equals 6, and we're going to solve for x. What will x equal if I shift the 3y to the other side? Negative 3y plus 6, or you could do 6 minus 3y, whichever you prefer. Okay, good so far? That's sort of this step 1 that's happening here. They're not numbered, but that's what I'm doing. The second one is to substitute that variable into the other equation. So I need to use the other equation. This is my step 2. And I need to replace the variable x right here with the quantity negative 3y plus 6. So right now, the 5 is multiplied by the x, but now my x value is negative 3y plus 6, so it will replace or get substituted in for x. Minus my 6y equals 23. Okay, so far so good? Okay, so at this point then, we're going to solve this equation. At this juncture, we have an equation that has only one variable. So we should be able to collect all the like terms together, isolate the y, in this case, all by itself, and solve for it. So we'll distribute the 5 through. So I have negative 15y. Distributed again, I have plus 30 minus 6y equals 23. So negative 15y and negative 6y is negative 21y. And what I'm doing is step 3. Step 3 actually says solve for it. Solve the remaining variable. We're doing that. So this is step 2. This one's step 3 that I'm doing right now. So then I have equals, what was it, 23? What would I do next? Move the 30. Yeah, I'll subtract my 30. It's currently added, so now we will subtract it. And I have negative 21y equals what? Negative 7. And the last thing I need to do at this point in the problem is, yes, and I'll do that with division, right? So how can negative 7 over negative 21 simplify? It's 1/3. It's not very nice, but it's nicer than negative 7 over negative 21. So this is my value for y. Exactly. So I can take either equation, if you wish, here, or even the one right here to solve for x. The one that's easiest to solve for x is this one, because it already has x equals, and it's solved for x. So while you can put it in anywhere, You actually get to make the choice of what's the easiest. It's definitely that one. So I have x equals negative 3 times my y, which was 1/3, plus 6. What's negative 3 times 1/3? Negative 1, and plus my 6 would give me 5. So I have found x is 5, I have found y is 1/3, and just like when we were talking about intercepts, we're talking about a point, right? This is a point in space. So my solution set, what I need to write down as my answer, is actually the ordered pair, in this case, 5, 1/3. This is my answer. Okay, x equals 5, y equals 1/3, we're portions of it, and then we combine them into a single ordered pair. How could we check to make sure it's right, besides flipping to the back of the book if it's odd? Yeah, you could plug the two values, 5 and 1/3, in for the x and the y in each equation, right? And if you've done it correctly, it should have a balanced equation so that both sides are equal in both of the equations. Okay, let's try another method. This one is, your book calls it the addition method. Most books call it the elimination method. I want to mention it in both ways because they actually both make sense. What you are going to be doing is adding equations together, hence it's called the addition method. But when you do that, things eliminate themselves, so hence they call it the elimination method as well. I will probably by default call it the elimination method because most of the resources I use call it that. So with this method, you're going to adjust the coefficients so that one variable cancel out when the equations are added. So what does that mean? Well, let me just flip over here so you can see. These are the 4 coefficients that are highlighted. What we want is we want either the x's or we want the y's to be the same number but opposite signs. And the reason is because what we want to do is we want to add them together and get them to eliminate each other. So in other words, my goal might be to get this to say 15x and negative 15x. I mean, I have to adjust the rest of the equation, but that would actually be the adjustment that would be one of the adjustments that would work. Okay, so that's what I'm looking for as I'm adjusting things here in a moment. So that's first step, adjusting the variables. So adjusting the variables simply means multiplying them by something that makes them easier to work with when we're considering them together. Then we're going to add the equations, hence why it's called the addition method. When we do that, something will eliminate. That's what we did in step 1, is we ensured that one of the variables will go away. And then, just like on the substitution method, we solve for the remaining variable, we substitute it back into one of the original equations, and we find the second variable that we didn't already know. So I'm going to suggest that we do exactly what I had mentioned before, which was to make the x value at the beginning have a 15. If I didn't choose to make the x values coefficient 15, what y value coefficient would also be equally good? Yeah, 14, right? Okay, so I need to make one of them positive and one of them negative, and it doesn't matter which one. I'm going to choose to make the first one negative and the second one positive. So if I multiply the first equation by negative 3, I will get negative 15x at the beginning. And if I multiply the second equation by positive 5, I will get positive 15x at the beginning. But as we multiply them, we have to multiply everything in the equation, all 3 pieces, not just the one that I'm trying to get to be the same. So I have negative 15x, I have positive 21y equals negative, what's 27 times 3? What is it? 81, thank you. Negative 81. I want one of them to be positive and one of them to be negative. My goal here in a minute, as I do this, let me show you, is that when I add these together, they cancel out. So it doesn't really have to be that the first one's negative 3. You could have the second one negative 5, but one of them needs to be positive and one of them needs to be negative to give me those different signs when I've multiplied. Sometimes the signs are already opposite when we start, in which case we don't multiply by negatives. Okay, on the second equation, my 5 times my 3 would give me a 15x. 5 times my 2y gives me a 10y. And 5 times 10 gives me 50. So my goal, which was to add these together and get them to eliminate, works. And then I add the remaining pieces together, sort of like addition from like first grade, right, where you just add straight down. So 21y and 10y would be 31y. Negative 81 and positive 50 would be negative 31. And when I divide by my 31, what's y? Negative 1. Sorry, there's the negative. Okay, so this was step 1 where I got my adjustment. That's what I was doing up here. Step 2 was adding the equations together, and then step 3 was the solving of what was remaining. I need to take this equation, or this expression's value, right? Y equals negative 1. And you can use any of the equations. This one is not sort of like the last one where there was a natural choice. The natural choice was to take the one that was already solved for x. Well, I don't have that here, so I just need to pick one. And there's probably not one in general that's better than the other on this particular problem. So I'm just going to take the top one, 5x minus 7, my y is negative 1, equals 27. If you do the second equation, you'll get the same answer. So this is 5x. Negative 7 times negative 1 gives me positive 7 equals 27. Then what? Subtract my 7. So these add to 0. 5x is equal then to 20. And when I divide by 5, what's x? Yeah, x is 4. And then I'm always going to write my solution as an ordered pair. X is 4. Y is negative 1. So this is my answer, my solution. So both of the equations we've done so far did in fact have a location that they had a solution for, right? As I'm solving them along the way, at the very end I get x equals something, y equals something, and we're good to go. So that happens most of the time, and it should make sense. What we're really finding when we're looking at two lines is we're finding the places where they cross, right? But not all lines cross. In particular, what kinds of lines don't cross? Parallel lines. So one option that we haven't seen just yet in the problems I've done is parallel lines. The other option that we haven't seen and might not necessarily come to your mind is what happens if they give you two equations that are really the same equation, just they look different, right? So that's a third option of something that can happen. So the last part of this section talks about classifying systems. So classifying it as being, it has one solution, like the three that we've done so far, or it has no solutions because the lines are parallel, or it has infinitely many solutions because the lines are really the same line, okay? So there are two different options here for classification. You can have systems that are consistent or inconsistent. So consistent means they have at least one solution. So everything we've done so far over here has been consistent equations, right? There are three problems we did. All three problems that we have done are consistent solutions because they have at least, or consistent equation because they have at least one solution. The other option is that we have a consistent equation that's really just the same line and there are infinitely many solutions. And then our last possibility, so it's either consistent and independent. Okay, that's what this one was over here. And all three of them. These are consistent and independent. Consistent because they have at least one, independent because they have exactly one. Yes?
Don't they have multiple because we solved the same set of equations and got different answers?
So not because we got different answers, but the same one. So I'm going to do an example of each of them and you'll see what happens for it to be the second system because we haven't seen it happen yet. But consistent and dependent really means it's the same line. Two equations that are the same line. So this isn't a very exciting one, but I'll make one up. Let's say you had x plus y equals 1, and then you had 5x plus 5y equals 5. That is the same line. Very obviously the same line. And if I gave you this system and you tried to solve it, you would very quickly find with any method that you have infinitely many solutions, and I'll show you that in a second. Inconsistent means no solution. No solution really means you have parallel lines. And an example of that that would be clearly not working for us is if you have x plus y equals 1 and x plus y equals 2. Well, it can't be both, right? These would be parallel lines, but very clearly this would not work. There is no number that I can create there where the x plus y is 1 and x plus y is 2. It's not going to happen. So let me actually show you with some less than obvious equations how this plays out. Now the reality is it plays out very much like what we've done before. What you're doing is you're going to try and solve them, and there's no directions on whether it has to be done with elimination or substitution, so you get to pick. I'm going to do these with at least this one with elimination, because as you take a look at the variables, you can very quickly see what you would need to multiply one of the equations by to make the nice numbers show up in front of either the x or the y. What number would you like to multiply by which equation? Yeah, and that's the only one we need on this particular one. Now, just because you've only got to multiply one equation doesn't necessarily mean this is going to fail. It could still end up giving you a single solution. But you don't always have to multiply both equations by a number. This one will work on the first only being multiplied. This gives me negative 4x minus 2y equals negative 18. Second equation stays the same. 4x plus 2y equals 10. But notice what's happening on this as I add down. What happens to the x's? They cancel. What happens to the y's? They cancel. So what I'm actually left with on the left-hand side is the number 0. There's nothing left on the left-hand side. If on the right-hand side it also says equals 0, then that means the lines are the same. But this one doesn't do that. What happens when I add the numbers together on the right-hand side? I get negative 8. And does 0 equal negative 8? No, this is a false statement. So if that happens, it means we have no solution. And no solution over here, you can see, means that the equations are inconsistent or that I have parallel lines. And it doesn't ask me to write it, but I'm going to write it anyway. These are parallel lines, just to remind you. Okay. So if I'm choosing to use elimination, and I end up having my x and my y cancel out, what I have to do is I have to look at the resulting equation. If the resulting equation is false, then it means there's no solution. If the resulting equation were true, right, if it said 0 equals 0, what this would mean is that this would mean that I'm in the case where I have a dependent system with infinitely many solutions. It would mean that anything that's a solution of the first equation is also a solution of the second. It doesn't mean that every x and y value work. It just means that if an xy pair works in the first one, it will also work in the second one. Every one that works in the first will work in the second. Let me actually show you what happens if you try to use eliminate or use substitution to do this type of a problem, because it could come up in either situation. Obviously, we could multiply the second equation by negative 5 and do the same thing we just did, right? Everyone, yes? And things would eliminate? Okay. So I want to do this with substitution so you can see what happens substitution perspective-wise. So very clearly, this is the equation and this is the variable if I'm using substitution that I want to solve for, right? Yeah. So I'm going to move my 2y to the other side. So there's negative 2y plus 120. And I'm going to substitute that into the equation up here for x. So I have 5 times negative 2y plus 120 plus 10y equals 600. Okay, everybody good so far? With substitution, we distribute things through. So now I have negative 10y. What is 5 times 120? 600 plus my 10y equals 600. Now what happens? Yeah, these 10y's eliminate, right? There's no more variable in my equation. However, so that's just like what happened over here. No more variables are in the equation. However, what number remains on the left? 600 actually, right? What number remains on the right? 600. And is this equation true? Yeah, that's a true equation. So while on the problem before, when I eliminated all my variables, I ended up in the equation that's not true. 0 did not equal -8. Here I end up in an equation that is true. Now, if you happen to subtract the 600 from both sides and it results in 0 equals 0, that's fine. It's still true, right? Would still be a true statement. This is true. And when that happens, whether it's done by substitution or by elimination, what it means is that there's infinitely many values, or many solutions, excuse me. And infinitely many solutions means that I'm in this case, consistent and dependent. So as I'm classifying this one is consistent and dependent. What's that?
It's the wrong one.
Oh, I'm on the wrong line. You're right, I am. Sorry. Cut. Thanks. There we go.
When we're writing that, we need to put consistent and dependent, or just
So to classify actually means that you're going to put one of three things, okay? So that's a very good question. Ooh, there's a bright screen. So when you were asked to classify, one option is that it's consistent and independent. Second option is that it's consistent and dependent. And the third option is that it's inconsistent. Okay? So it's one of those three descriptive phrases, yes. So we actually saw three problems at the beginning that were all consistent and independent. And then we did examples at the end, two other ones that were either consistent and dependent, that was my last one, or inconsistent, which was number 4. Any questions on those? Okay. Well, technically I could start the next lesson. I don't think it's worth it for 5 minutes, so I'll record that video as a whole from when I've done it before for section 5.2.